Hello everyone. Today we are going to start about the topic revised simplex method in the optimization techniques. So it is a advanced topic rather than the simplex and graphical, two-phase and begin. So this method is the simplex that is easy methods which updates a simplex table quickly moving from one iteration to another. That is, and in this revised simplex method, it is an advanced method, and this revised simplex method has two standard forms. That is standard form 1 and standard form 2. So that is in standard form 1, it is assumed that the identity matrix is available after adding slack variables and there is no need of artificial variables. And but in standard form 2, it also added in order to have the our identity matrix, that is the artificial variables are added in order to have the identity matrix. So we just start with the device simplex method in standard form 1. But you know that in the mathematical formulation, you have the objective function and the constraints and restricted constraints. So in the simplex method, the basic step is we just make it into a standard form. So here also we just want to make it into a standard form, but in one change, that is we are just including the objective function as one of the constraint in the standard form. So the basic step which we are doing in revised simplex in standard form 1 is we just have your the canonical form, that is max z is equal to c1x1 plus c2x2 and so on cnxn, and subject to the constraints a11x1 plus a12x2 plus and so on a1 and xn equal to, or in canonical form you'll be having either, if you're having objective as max z and which is in the constraints you'll be having less than or equal to b1 and so on am1 x1 plus and so on a mn xn which is less than or equal to bn, and finally you are having the restricted constraint as x1 x2 up to xn plus m or xn which is greater than or equal to 0. So in this canonical form, we just want to make it into a standard form. But while doing in revised simplex, we just include the objective function as one of the constraint. So we just rewrite this objective function as max z is equal to c1x1 plus c2x2 plus cnxn, and plus we are adding the slack for making the constraints to a standard form. While adding a slack, that is the first slack to the first constraint, if it is xn plus 1, because in the first row you are having a11x1 plus a12x2 plus and so on a1 and xn. If you are adding the slack xn plus 1 with the first constraint, and we just make this inequality into equal, so which is equal to b1. While adding a slack variable, we just introduce the cost as 0, so we just add that variable with the objective function also with a 0 cost. So that's why we are adding 0 x n plus 1. And for the second constraint, we'll be having a21 x1 plus a22 x2 and so on a2 and xn, and adding the second slack variable xn plus 2, and the inequality less or equal to is becomes equal to b2. Like that, you'll be having the final row, that is the mth dimension, as am1 x1 plus am2 x2 and so on amn xn plus xn plus m is equal to bm. So these b1 b2 and so on bm are the solutions, and this a11 a12 and so on a1n are nothing but the coefficients of this augmented matrix, and this x1 x2 and so on xn are the decision variables. And here by making it into a standard form, you'll be having the slack variables xn plus 1 xn plus 2 and so on xn plus m. So we just have all these are non-negative. We are having the restricted constraints as the decision variables x1 xn plus 1 or not negative. So that's why we are writing this as greater than or equal to 0. So first we just, you are having a formulation, that is if you are having a real life situation. So you making that real life situation into a mathematical formulation, After making into a mathematical formulation, we just want to solve it. For solving this, we have several methods. So instead of all the methods, we just going for the revised simplex method. And in that revised simplex method, the first step is we just make this formulation into a standard form. So for standard form, what we are doing is we just add a slack variables. That is, if you're adding a slack variable, and we can make this inequality to equality with the zero cost. So we just add all these variables into the objective function with the zero cost, and also included all the slack variables are restricted, but all are non-negative. So that is the first step. And the second step, what we are doing is we just make this objective constraint objective function as one of the constraint. So already you have your constraint. So if you are for the revised simplex method, we just include the objective function as one of the constraint. So we have, that is, the basis matrix B becomes M plus one dimensional, right? Because already you have a the basis is the, yeah, how many basic variables you'll be having? You have only that is x1 to xn. But if you are adding one of the constraint, that is the objective function as also one of the constraints, so you'll be having your m plus one, yeah, one dimensional. So after making into a standard form and including the objective function as one of the constraint, so that is your first constraint. Let's see this one. See here. So you have z minus c1x1 minus c2x2 and so on, which includes the zero cost of the slack and which is equal to 0. So because you are having your objective function as max z is equal to this much. So if you are writing it into a solution, it will become z minus of c1x1 minus c2x2 and so on, minus cnxn minus 0 into xn plus 1 and so on, 0 into xn plus m, which is equal to 0. So that is the first constraint. And the remaining constraints as well, you know that. That is a11x1 plus a12x2 and so on, a1 and xn minus 0x, what is that? Not minus. It should be plus 0xn plus 1 and so on, which is equal to B1. Because the remaining elements which has the there is a coefficient 0. So likewise, you just write on all the constraints and also the restricted constraint. So after writing it into a standard form, which includes the objective function as one of the constraint. After writing that, as usual, we just want to write it into a matrix form. So after writing the matrix form, you'll be having this z minus cx equal to 0. That is your first constraint. Sorry. That is z minus c or nothing but the cost variables, and x is a decision variable. And the second one, you have the coefficient matrix ax is equal to b. That is your a or nothing but the coefficients, and x is nothing but the decision variable, and b the solution, and x greater than or equal to 0. So simply we are writing the matrix form as like this. And after writing it into a matrix form, we just have the format as if you're writing the coefficients alone in the matrix form, that we know, right? Because if you're having a simultaneous equation, we just want to write it into a matrix form. The coefficients are in the first matrix, that is augmented matrix, and into the column matrix, that is the decision variables are representing in the column matrix, which is equal to the solution, that is also a column matrix. So here your matrix are like this: 1, a01, a02, and so on, because the coefficients are representing as a01, a02, and so on for your z. Like that. And if you are writing it in a simplest form, that is nothing but 1, a0, 0, and capital A as in 2 by 2 matrix, and the vectors, that is the decision variables are representing in the column vector, that is x0 and x, and the solutions are representing in the again the column matrix, that is 0 and b. So in a simplified form, if we are again rewriting this as in the matrix, is 1 minus c, 0, and capital A. Is 1 representing the unit vector, and minus c representing the cost, which is in the objective function, that can be represented in a first row, and the remaining column, the remaining rows are Nothing but the first column should be the zero vector and the remaining are nothing but the coefficient matrix. That can be represented as capital A. And the vectors, the first row, it is for the Z. So it is Z and the remaining variables are representing as X, which is equal to the solution matrix that is 0 and B, right? And after representing this, we are just want to write it down the basic matrix. So before making into a basis matrix, we just want to find it out the linearly independent column vectors. So if you see this matrix, if in this matrix, so these are the columns, excuse me, these are the columns representing into a linear, that is, it's just making into a linearly independent column vectors. So that are for the slack variables, that we know that, right? So for these variables are representing as the basic variables. So for as usual, we just want to find it out the initial basic feasible solution. So after making this initial basic feasible solution, we have the remaining non-basic variables, that is x naught to xn, right? So this x naught to xn are nothing but the non-basic variables. So these columns are represented as an additional table while calculating in revised simplex method, right? So what we are going to find it out is, we just want to find it out the initial basic matrix and the additional column, that is additional column or nothing but the vectors which are not in the basis. So we just represented the vectors which are not in the basis can be, or it can be represented as an additional table and which are not in the basis. So we just consider only the basis matrix. So if you are considering the basis matrix, we can have this as B1 inverse, because in this revised simplex method, we just calculating only the B1 inverse, right? No need of the calculation of all the column vectors which we have done in the simplex method. So here this is a simplified method and the advanced method. So for this we can calculate, or we can that is using the elementary row operation, we can calculate only the inverse of this B1, that is B1 inverse. So B1 inverse is nothing but again the matrix 1 CBB inverse and 0 B inverse, 1 representing the identity element, that is unit identity element, and CB is nothing but the cost of the basis, and B inverse is nothing but the inverse of the basic matrix. That's the basis elements which are having a linearly independent column vector. So always the basis matrix which form an identity matrix, the base using the basic values which we are having identity matrix, that is said to be basis. So we can find it out your basis inverse. So for calculating, that is here, we don't want to need all the columns. We don't want to calculate it for all the decision variables. That is in iteration table, you're having y1, y2 and so on, yn. But for doing the revised simplex method, you don't know, no need to calculate all the columns. We just only calculate your B1 inverse. With that B1 inverse, we just find it out your yj inverse and the xb inverse. Xb inverse, x, or not xb inverse, xb. Xb is nothing but the basic solution. The basic solution, we can find it out, which is as P1 inverse into B. So from the net evaluation, we just concluded the optimal solution, right? So for finding out the Cj minus Zj, Cj minus Zj is nothing but the net evaluation. So if all the, we just want to conclude with the net evaluation for the optimum solution. So here, no need to calculate all the columns. So instead of making all the columns, we just find it out the first row of B1 inverse into the column vector which are not in the basis. So if we are having a product of first row of B1 inverse into the column vector which are not in the basis, we'll be getting your net evaluation. So if the net evaluation without with the net evaluation, we can terminate the problem, terminate the iteration. If it is not satisfies, then we can find out the improved optimal solution. So these are the basic steps, and with that, first row of B1 inverse, and with this we can find it out the corresponding Yj vector. That is, this Yj vector is nothing but the vector which is inserting, which will be, or which has been inserted in the table. So for this Yj, but in simplex method, we just want to find it out all the columns and the minimum ratio, like that we are doing that. But here also we just want to find it out the minimum ratio and all. But for finding out the minimum ratio, we just want to have your Yj. Yj inverse is Yj is nothing but, or how can we find it out? We can use your B1 inverse into AJ1. But here we just, this J representing the vector which is to be inserted. Right? Okay, so with this calculations, we can easily solve the linear programming problem using revised simplex method. So these are the basic steps, and in the next video, we'll see about the computational procedure and algorithm. Thank you.